Now let's get back to Newton's second law, which says that if you have a particle, then sum of the forces applied on a particle is equal to mass times acceleration. And we all know this equation very well. But we have to be careful before we apply this equation. We cannot use this equation when our reference frame is an accelerating one. So this equation is actually valid only if acceleration is measured in an inertial, or also known as Newtonian, frame. And by definition, an inertial or Newtonian frame is a non-accelerating frame. So if you're trying to use this equation and you measure the acceleration with respect to an object that could be potentially accelerating, then you will be making a mistake. So let me give you a simple example. So let's say there is an elevator, and inside this elevator you are standing, let's say we'll call you A, with your friend B. Okay, and this elevator is actually moving up with some acceleration, let's say A0. And your friend, he is engineering dynamics class, so you ask him to analyze the motion and the forces on you. So what he's going to do is he's going to do a simple application of Newton's second law on you. So he starts by drawing a free body diagram. So that's you over here. Okay. So he says, okay, we know what your weight is. That's ma times g, and the normal reaction from the elevator on your feet is, let's say, n sub a. Okay, and these are the only forces that are acting on you. And he says that I'm standing right next to you and I'm looking at you and you're not going anywhere with respect to me. So I'm going to write sigma f is equal to 0 because I don't see you going anywhere, right? You're standing right next to me. There's no motion of you with respect to me. And he concludes that NA minus MAG, assuming that upward is a positive direction, is 0. Okay, and that means NA is equal to MA times G. So he says that the normal reaction on your feet is same as your weight. But you know that if you're going up in an elevator that's potentially accelerating, then you feel actually heavier, right? You feel more weight on your feet rather than when you stand still inside an elevator. So this analysis would be perfectly fine if, let's say, the elevator was not moving, it was not accelerating. But this is clearly not right? There is some problem with this analysis. So now the question is, what is wrong with this analysis? What is wrong is that your friend B is basically measuring the acceleration of you with respect to himself, and he is inside the elevator that is traveling with an acceleration. So essentially, the reference frame that is attached to measure the acceleration is actually a non-Newtonian one. This is a non-Newtonian frame, which you cannot use to apply Newton's second law. So how would this analysis be fixed? Well, it's really very simple. He would have to step out of the elevator, okay, essentially turn himself into a Newtonian or an inertial reference frame. So we'll draw this again. There is U, which is A, and now B is actually standing on the ground, right? And this is the reference frame, and this is a fixed reference frame, which means that the acceleration of this frame is actually 0 because this frame is not moving. And now he draws a free body diagram once again, which is not going to change, by the way. So we'll call it NA prime. And of course, your weight is still same because that's the gravitational pull from the center of the earth on you. And now he says sigma f is equal to m times acceleration. And we have forces on the left-hand side. On the right-hand side, we have m times acceleration. Now the acceleration of A will be same as acceleration of the elevator. Acceleration of the elevator, because you're not moving with respect to the elevator. So this is m times a0. And remember, upward is a positive direction. That's why I'm writing na prime first. And a0 is positive 2 because upward is positive direction. So na prime now is mag plus m times a0, which can be written as, this is ma times g plus a0. And that makes sense because now you can see clearly from this equation that you will feel heavier when you're going up in an accelerating elevator. If A0 is equal to G, then you'll feel twice as heavier than you are if the elevator is standing still, right? How would this change if, let's say, you were going down with some acceleration? Well, the only change would be really in the sign of the acceleration. So instead of positive, this would actually be a negative quantity, and that means here we will have a negative quantity, and this would change to a negative quantity too. So now you can see that you will actually feel less heavier or lighter if you are going down with some acceleration. And if A0 is equal to G, you will actually feel no weight whatsoever, right? And that's called basically the free fall condition, not the sort of condition that you ever want to be in when you're moving inside an elevator, right? So this simple example basically shows you that if you measure the acceleration with respect to an accelerating frame, then you will make mistakes, and that's a problem. Another example I will give you is, if let's say there is a wedge and there is a block on it, okay, and you might see, some examples or problems in your textbook that look something like this, okay, and A is moving down the incline, okay, so B is allowed to move, and let's say B moves this way with some acceleration AB, while A comes down, okay, along this incline and is moving downward, and you're looking to do analysis on A. Okay, so to do the analysis on A, you know that you have to draw a free body diagram, right? So you will show the normal reaction from B on A, we'll call it NA-B, to indicate that's an interaction between A and B that is giving rise to this normal reaction. And this normal reaction is, of course, perpendicular to the direction of the incline, right? And then you have the weight of A, MA times G, and let's say there is some friction between the two surfaces, so you also have mu K times NA dash B, right? So that's your kinetic friction force, because we know for sure that there is sliding happening between A and B, okay? So these are all the forces acting on it, and you have tried to apply your Newton's second law to this particular problem. You say sigma F equal to MA, right? So let's write that. So we have sigma F equal to mass of A times acceleration of A. Okay, so sigma F part is clear, right? So let's say we pick our coordinate system to be looking like something like this, X and Y, all right? So sigma F part is easy. You can resolve each of these forces. If you know this angle, you can resolve each of these forces along X and Y direction, and you can write your left-hand side, right? That's the sort of stuff that you did a lot in your engineering statistics class. Now let's focus on the right-hand side. We have a mass of A times acceleration of A. Now the question is, what is acceleration of A? Now you can clearly see that A is moving relative to B in this direction. So would it be fair to say that that is the acceleration of A? That is the direction of the acceleration of A? So could we write this? Could we say that acceleration of A is equal to whatever the magnitude may be, and its angle is minus cosine theta I hat, and I'm resolving it along X and Y direction, right? So let me draw this again. So I have my X direction, I have my Y direction, and I have my acceleration vector AA, which is pointing at an angle theta from horizontal. So I get minus cosine theta I hat minus sine theta j hat. That's the unit vector, right? So would it be fair to say that this is the acceleration of A? Well, clearly this is not right, because this is the acceleration of A only with respect to B, right? So if you were a frame, or if you were an observer who was standing right on B, this is the direction of acceleration of A that you would see with respect to yourself. And that is basically relative acceleration. So this is really not the acceleration of A. Okay, this is acceleration of A relative to B. That's what this is. So if you were to take this acceleration and plug this into the Newton's second law on the right hand side of the Newton's second law, then you will be making a mistake. So what is the right way to solve this problem then? Well, the right way would be to say that here is my reference frame, which is going to be either fixed or it could be moving at constant velocity. Remember, the Newtonian frame or inertial frames are non-accelerating. So non-accelerating frames could arise either due to no movement, no motion of the frame, or due to constant velocity, because constant velocity also gives rise to zero acceleration. Okay, so in the previous problem over here, you could have your friend B actually move inside another elevator moving with, constant velocity. So this is constant, which means acceleration would be zero, and that would give rise to the same results as you get if, let's say, the frame is not moving at all. So constant velocity or no movement, both of them would give you the same result. So coming back to this problem, you would have to really attach your reference frame to either a constant linear velocity object or to a fixed object. So if you do that, then the acceleration of A would not be equal to this, what you have written over here, but acceleration of A would be equal to, now you would have to use the relative acceleration formula over here as the acceleration of B plus acceleration of A related to B. And acceleration of B is clearly along x direction, so that would be some magnitude times I hat plus this quantity, which you would write from here. Okay, so the basic summary is that do not use this equation sigma f equal to ma in a non-Newtonian or a non-inertial reference frame. Make sure that if you are measuring accelerations, you are going to be measuring acceleration with respect to a frame that is either not moving or is moving with constant velocity.